In this lab, I'm going to apply Newton's second law and the energy principle to simulate a spring's oscillation as it is dropped from rest at an angle. The system will include the spring, mass, and earth. I will compare the results of the model to the results from analyzing the observed motion in Tracker to observe how well the program can model the spring's motion. For the model, I will assume energy is conserved, there is no air resistance, and the spring is massless. I tracked the motion of the mass at the bottom of the spring, as can be seen here. The mass oscillates. The graph on the right shows the change in the x direction as periodic. This is also the case for the change in position in the y direction. Using the position data from Tracker, I calculated the oscillation periods for the position in the x and y directions. The period in the x direction is 1.638 seconds and is greater than that for the y direction, which is 1.5428 seconds. Although some of the difference might be attributed to human error in selecting the mass in Tracker, their difference mainly reflects that the change in position in the x and y directions is not determined by the same factors. The y period is determined by how much the spring stretches or compresses, which is determined by the spring's stiffness K. On the other hand, the x period is determined by gravity, which depends on mass. To create a computational model for the spring's oscillation, I added the ball's mass, initial position, and initial velocity, which was 0 because it started at rest, and delta t at the bottom. I also added the following constants. The ball's mass spring constant and relaxed length of the spring were given by the video. I added the following lines to determine the spring force later on, the length of the spring and the direction of the spring's stretch or compression, and S, the difference between the current length and the initial length. Then I added the gravitational and spring forces to calculate the net force. Based on Newton's second law, which relates net force to momentum times time, I added the following equations to update the velocity and position based on the net force, which changes over time because the spring force is non-constant. Because the spring force is non-constant, I also update it here as part of the iterative while loop. To determine the changes in energies in the system, I use the energy principle, which relates change in total energy to the work done by the surroundings on the system. In this case, the system is the spring, mass, and earth, so the work is 0, which means the change in total energy is also 0. Here are the equations used for the kinetic energy, gravitational potential energy, and the spring potential energy, which are included in the total energy. Here I added the previous equations to calculate the kinetic and potential energies as well as the total energy in the system. To plot the changes in energy as the spring oscillates, I updated the values for the kinetic, potential, and total energies as the ball's position changes. When I run the model, the mass is seen to oscillate with the spring. The plot of the comparison of x position data shows that the model and experimental data are fairly well aligned, but become less aligned as the iterations continue. Also, the amplitude of the model's position data is greater than that of the experimental data. Similarly, the comparison of the y position data shows that the model has a greater amplitude than the experimental data, but the oscillation periods are fairly well aligned. The differences between the model and experimental position data might be explained by our assumptions of no air resistance and the spring not having mass, as accounting for these in the model would affect the motion of the spring and change the position data. In the energy graph produced by the model, delta E is equal to 0, and as can be seen by aligning this line to the curves, the change in kinetic energy, change in gravitational potential energy, and change in spring potential energy add to 0. As the change in kinetic energy starts to have a smaller amplitude here, the change in both potential energies change correspondingly. So for this model of the system with my assumptions, the model satisfies the energy principle.